Okay, thank you. Am I too loud? Okay, thanks very much. So I want to continue what I was talking about yesterday. So we have these orbit spaces, orbits of group representations that correspond in a natural way to certain arithmetic objects. And so I wanted to talk about some of the applications of having such parameterizations, particularly to arithmetic statistics. So this is the last thing that I didn't talk about yesterday, density theorems. So understanding basically the distribution with respect to basic invariance of some of these arithmetic objects that come up as the objects being parameterized by the orbits of these group representations. So this actually has a history. So I mentioned that there were two examples of these parameterizations known before. The first is Gauss composition on binary quadratic forms, and the second being the Delaunay-Faddeev correspondence with orders in cubic fields. So let me first show you. So this, as I said, so Gauss composition in the space of binary quadratic forms already had an application due to Gauss to arithmetic statistics, namely the following result. So if you look at the class numbers of imaginary quadratic orders, okay, so if you take the quadratic order of discriminant d, or I guess minus d, okay, so let minus d be a number that's 0, 1 mod 4, then you can talk about h of minus d as being the class number of the quadratic order that has discriminant minus d. And you want to know how big do you expect that to be as d varies. Okay. So what Gauss conjectured in his disquisitiones is that if you take this class number, h of minus d, over all d between 0 and x some large number, and you sum them, then that grows as a certain power of x, namely x to the 3/2. And as Henri mentioned yesterday, h of minus d we expect to be on the order of about square root of d. So if you sum square root of d over all d between 0 and x, you expect something around x to the 3/2. And what Gauss says is that's exactly true, and with a very particular constant, namely pi over 18 zeta 3. And so this is what, so this is something that Gauss conjectured in his disquisitiones. And how did he conjecture this? Well, he doesn't really say, but my guess from reading it is that, well, he developed a reduction theory for binary quadratic forms. So he said, let's look at the space of all real quadratic forms, or quadratic forms over the real numbers. So that's three-dimensional, but I can only make a two-dimensional picture, so pretend there's 3 dimensions. Okay, and then he developed a reduction theory. So you take real quadratic forms, so in other words, binary quadratic forms with real coefficients, and you have GL2Z acting on it, this discrete group acting on this three-dimensional real vector space, and he constructs an explicit fundamental domain for this action of GL2Z on real binary quadratic forms. And so I've made kind of a picture of that. So this fundamental domain looks something like this. So it's the stuff between these two lines, so this line here and this line here. So maybe I should have erased. Okay. So it's the stuff between these two lines. And then he says, okay, the integer points inside this fundamental domain are going to be what he calls the reduced forms. Okay? And he wants to know how many reduced forms are there of discriminant less than x, of absolute discriminant less than x. So you draw the condition that the discriminant is less than x. So everything inside here so everything inside this region will then be all the reduced forms that have discriminant less than x. Now, so that's some region in three-dimensional space, and if you count the total number of lattice points in that three-dimensional space, then you should get the answer. And he computes the volume of this thing, and you find that it's pi over 18 times x to the 3/2. That's the volume of this region, and so you expect that that's how many integer points, how many lattice points you'll have inside that region. So the number of lattice points inside a three-dimensional region you kind of expect to be the volume of that region. And so that's kind of what I suspect he was arguing. The reason that it's not a proof is that this three-dimensional region where he's counting integer points is not compact. it goes off to infinity. So you have this three-dimensional region, namely the set of reduced forms, where the discriminant is less than x. It has finite volume, which he computes, being pi over 18. But because it's not a compact region, there's this cusp that goes off to infinity. It's entirely possible that that cusp contains lots and lots of points. It's entirely possible that the cusp contains no points. It may have nothing to do with the volume. Right? So I wonder if there's, okay. Is there chalk here? No, over here. Big. No, sorry? Yeah, so if you have a compact region, like, so if you're counting the total number of points where x squared plus y squared plus z squared is less than n, right, then you just have a big ball. Yeah, that's a different sum. So if you have a compact region that's sort of growing homogeneously, the number of integer points you expect in there is going to grow like the volume. But if you have a non-compact region, then it is entirely possible that you get lots of and you let this homogeneously expand, it is possible that you get lots of points in the cusp. It's also possible that you get no points in the cusp. And the relation, so in the compact part of the region, you expect the number, well, you can prove that the number of integer points grows like the volume. That's Riemann integration. But in the cusp, you don't know what's going on. And so you have to analyze what's going on in the cusp and actually to prove the assertion that the number of integer points in here that correspond to irreducible binary quadratic forms actually grows like the volume of this thing. And that's something that was proven by Mertens. So it was conjectured by Gauss, but Mertens proved that the number of integer points in here becomes negligible, the ones that you actually want to count. And so he argued that you can cut off the cusp at a point such that you have negligible volume as this grows, and you argue that the number of integer points that you care about actually grows as the volume of this non-compact region. So that's due to Mertens. And since there's one thing I neglected to mention, which is that ideal classes that are invertible, when you talk about the class number, you're actually only counting invertible ideal classes. And so if you're only interested in invertible ideal classes, then you're actually only interested in primitive binary quadratic forms, those that don't have any common divisor of the coefficients. And so that's what leads to the zeta 3 here. If you only count primitive things, then you get a zeta 3. And so, but if you let h minus d denote all ideal classes, count of all ideal classes, then you'd get pi over 18 times x to 3 halves, and pi over 18 is actually the volume of this region that Gauss actually computed in his disquisitiones. Okay, so Mertens actually proved this 50 years later by analyzing the cusp of this geometric region. Okay, the other case, other parameterization that was known previously, the Delaunay-Faddeev one, for the correspondence between binary cubic forms and orders in cubic fields, you can do a similar count there, and that was done by Davenport and Heilbronn. And in around the 1960s, Davenport started the count of binary cubic forms, and then this application to cubic fields was done by Davenport and Heilbronn. And so they proved that the number of cubic fields of absolute discriminant less than x is 1 over zeta 3 times x. And again, the argument goes similarly. They make a fundamental domain. So they make a fundamental domain for the action of GL2 on binary cubic forms. So now this is a 4-dimensional space instead of a 3-dimensional space, even though I keep drawing it in 2 dimensions. Right? And again, it's because it's the same kind of group acting, the shape of the fundamental domain, because it's the same group GL2Z or SL2Z acting, you get a fundamental domain that's similar. It has one cusp that goes off to infinity. And then they put the condition that the discriminant is less than x. And they want to count the number of integer points in here. Right? And that'll tell you the number of binary cubic forms up to GL2Z equivalents that have discriminant bounded by x. But this time, the cusp, because it's 4-dimensional, with the same group acting, this cusp is quite a bit more complicated than the one in binary quadratic forms. And that's why it took so many years. I mean, Davenport had to introduce many additional ideas in order to deal with this cusp. One problem is that you get actually many reducible binary cubic forms inside this cusp. In fact, the order of magnitude of the number of reducible binary cubic forms that show up in this cusp is the same as the number of binary cubic forms in the main body. So that's not something that happened in the binary quadratic case. So a lot of additional work has to be done to show that even though there are lots of points in this cusp, they're not points that you're interested in counting. Namely, they're all reducible. They factor over Q. They don't correspond to orders in cubic fields. They correspond to orders in reducible cubic algebras over Q. And so what they argue is that everything in here, only a negligible proportion of the things in here you're actually interested in counting because they're reducible. And whereas most of the things in here are irreducible, and so they do correspond to orders in cubic fields. And so they argue that you just have to take the volume. You can cut off the cusp and say, OK, the number of integer points in the region that you care about is growing like the volume. And they compute the volume. So the volume, which is pi squared over 72 times x, gives the total number, the asymptotic number of irreducible binary cubic forms having discriminant less than x up to GL2z equivalence. And then, so this is the asymptotic number of cubic orders up to isomorphism with discriminant less than x. And then what they do is they have to do a sieve to maximal orders. And that's what leads to the 1 over zeta 3 is the sieve. So 1 over zeta 3 times x, that's the asymptotic number of cubic fields. It's up to isomorphism of discriminant less than x. So that's the argument. So again, most of the work is here in this cusp, understanding what's going on in the cusp, showing that even though there are lots of points in here, they're not points that you care about because they turn out to be reducible. For example, so the things in here turn out mostly to be orders in algebras of the form Q direct sum a quadratic field. So this is degree 2. So most of the stuff in here, by a wonderful coincidence, it's hard to count points in here, but on the other hand, they correspond to kinds of things that you could count easily by other methods anyway. There's just a count of quadratic fields up to discriminant x. So that's what happens to be filled in the cusp, and the stuff that you don't care about all lies here. The stuff that you care about all lies here, and here you can do the usual Riemann integration argument. So that's kind of how Davenport-Hilbrand works. Okay. So these are the two cases of applications of these group representation orbits to sort of important problems in arithmetic statistics. Okay. Yeah, exactly. Yeah. So Gauss wrote down very explicit ones, namely that the middle coefficient is bounded in absolute value from the first, less than the first coefficient, and the first coefficient is bounded in absolute value from the third coefficient. So that's fairly explicit for Gauss, and Davenport and Hilbrand also very explicit. These are defined by degree 4 inequalities, and they write them down explicitly, and they actually compute the volume using those explicit equations. Yeah. And then they analyze this cusp by showing exactly what what's bounding the cusp. They write down the explicit algebraic equations, inequalities that define this, right?
Can you give some reason why there aren't good points in the cusp? Why all the points in the cusp?
Yeah. I mean, they do it very, very explicitly. So they say that, I mean, what you end up showing is that if you're not a sort of a generic kind of cubic order, then you're going to be there's going to be some hyperplane, hypersurface that you'd be contained on, and that hypersurface, they figure out that hypersurface, and they find that it sort of intersects this fundamental domain that goes down into the cusp.
So that shows you that all those reducible points are in the cusp, right?
That's right. Yeah.
And so how do you show that there aren't other good points?
You mean there aren't bad points in here? No, there aren't good points in here.
There aren't missing points.
Oh, because this is getting so thin, and you have all these integer points along that hypersurface that you couldn't. So there's not enough room for then the good points to sit. Yeah. Yeah, exactly. And then, as I mentioned, this duality yesterday, the duality between cubic fields and 3 torsion and quadratic fields allowed them to prove these results about the class groups, which confirm cases of the Cohen-Leinster heuristics. Right? So the mean size of the 3 torsion subgroup of the class group of real quadratic fields turns out to be 4/3, which agrees, as Henri talked about yesterday, with the Cohen-Leinster heuristics. And another case, in the case of imaginary quadratic fields, that average of the total number of 3 torsion elements in the class groups of imaginary quadratic fields is 2. So these things are consequences of this work on binary cubic forms. Using the duality, either the class field theory duality, or you can actually just use the representation theory duality that I talked about yesterday, the elementary version, to prove these results, using the same binary cubic count. Okay, so these are the 3 sort of theorems that were known before in this kind of way. But now that we have all these additional parametrization spaces, one can now try to apply the same techniques to these larger spaces. So for example, right, we had the space that parameterizes quartic rings, and so one could try to count the total number of quartic orders by doing the same thing, trying to do the same thing. The problem is that, so this was already, if you look at the computations, already the computations are very huge because the algebraic inequalities defining the fundamental domain are degree 4 in 4 variables. And now, well, this space here is 12-dimensional. That's parameterized in quartic rings. And so if you try to write down inequalities for a fundamental domain for the action of GL2 cross GL3 on this space, it's going to be, first of all, in 12 variables. And it's not degree 4 anymore, it's degree 12. The equations defining the fundamental domain. But I did do this in my thesis, just in one case, in the totally real case. And I realized in hindsight it was a terrible thing to do. But I actually wrote down degree 12 inequalities in 12 variables in the totally real case. And okay, so here's a 12-dimensional picture that I'll draw in 2 dimensions. So I write down these inequalities, and here's, so it's this big fundamental domain. It has 3 cusps going to infinity instead of just 1, because it's GL2 cross GL3 acting. And so you have this fundamental domain that kind of like that. Okay. So it's all this stuff in here. Okay, so all that stuff is the fundamental domain. And then I said, okay, now let's let the discriminant be less than x. The discriminant is also a degree 12 function on this 12-dimensional space. I spent several months writing this down. And again, now you want to analyze the cusps. And I looked at one of these cusps, and it gets worse than the binary cubic situation. There are more points in the cusp than there are in the main body. And so that was horrible. But in the end, what happens is I've gotten used to it now that it's happened in dozens of cases that you just expect it to happen. But all the cusps contain things that you wouldn't want to count anyway, is what you end up proving. So for example, this cusp that has more points than the main body corresponds to orders in a quadratic algebra, direct sum of quadratic algebra. So all the points in here correspond to orders in quartic algebras. That's what this parametrization is telling us. And in one of these cusps, you get mostly points that correspond to orders in quadratic algebras, direct sum quadratic algebras. And of course, the main work is showing that you don't get too many orders in quartic fields in here. You get a negligible number of orders in quartic fields, and that does turn out to happen. So you just so eventually you can snip off this cusp once that analysis is done. In the same way over here, you can snip this off because this turns out to just be orders in Q direct sum cubic. And so again, those could have been counted by Davenport-Hilbrand, and so you don't need to bother with those. The reason that this is bigger, right? If you count the total number of quadratic direct sum quadratic having discriminant less than x, right? That's going to be like an x log x, right? Because these can go sort of independently. And what happens in here? Here you do get orders in quartic fields, so this frightened me a lot because how are you going to count stuff there? But it turns out these are orders in quartic fields, but the quartic fields have a restricted Galois group. Namely, they're mostly D4 quartic fields. So these turn out to be just orders, and so you don't get S4 ones here, you get D4 ones. And fortunately, one can count those separately anyway, too. This is work of Cohen, Diaz and Olivier, as Henri talked about yesterday. So all the cusp things, they're hard to count by geometric methods because they're going off to infinity and they're very sort of complicated geometrically. But they can be counted by other methods. And they weren't the ones that we were interested in anyway. From this point of view, we're interested in the S4 quartics, which are sort of the generic guys. And they all lie in here. So all the S4 quartic orders lie in here. And again, you have to argue that within here, you get very few of the things of the kinds of algebras that you see in the cusps. And so you snip off these cusps, and then you argue that the number of points as this expands grows as the volume of this region. And you compute the volume of the region, and you find it's zeta 2 squared. So the volume is equal to zeta 2 squared times zeta 3 over 24 times x. And that's the total number of pairs, order in quartic field, cubic resolvent ring in the cubic resolvent field. That's the total number of pairs is this. And the reason is because the cusps, we were able to argue, don't contain the kinds of points that we were interested in counting.
Do you obtain other Galois groups in the main body?
You do, but you show that they're negligible compared to this main term. Yeah. And now you have to do a sieve to get rid of, first of all, this weighting by the number of cubic resolvent rings, and second, you want to go to maximal orders, just like we did before. So sieve to maximal then allows you to give an asymptotic count of the total number of quartic fields of bounded discriminant. And so that's this theorem here.
So how do you compute that volume? Manipulating the rule of 12 degrees uniformity?
The volume, that's what I tried first, and I failed. So there's a trick, which I'll talk about a little later. Yeah. So the point is that because it's a prehomogeneous vector space, and there is a group acting, what you can do is you can start with a point, and you let the group act. You let a fundamental domain, namely GL, well, okay, the group is GL2R mod, the group is GL2R cross GL3R. So since it's a prehomogeneous vector space, this point can be taken to every other point in the fundamental domain by an element of the group. And so one figures out what the Jacobian of the change of measure is from this space to the group. And then one uses Haar measure. And that allows a very natural interpretation. So some of you probably know, right, the volume, the Haar measure of GL2R mod GL2Z is zeta 2. Right? And the analog for GL3R mod GL3Z, the Haar measure of that is zeta 2 times zeta 3. And that's where this comes from. And so this gives a very natural interpretation of the constants that come out in the volume. And in the Davenport-Heilbronn case, right, we were getting a zeta 2. And that came from this complicated integration involving these degree 4 inequalities. But really, this is just a Haar measure of GL2R mod GL2Z. That's really where that was coming from. So the volumes have natural interpretations in terms of Haar measures of these algebraic groups that are acting. And we'll see a lot more of this. S4 quartic fields. Yeah, that's right. Oh, yeah, absolutely. Thanks. So the number of S4 quartic fields, so quartic fields that have Galois closure with Galois group S4, turns out to have this asymptotic right there. Okay, and similarly, there's a quintic space, and that space is 40-dimensional. So with the group GL4 cross GL5 acting. I don't know if I should show it. Yeah, I'll show it here. So this was the quintic space over here. So this space is 40-dimensional. You have to do a 40-dimensional fundamental domain, and that was, okay. So writing down degree 40 inequalities and 40 variables, that I eventually realized was not going to happen. So a new method had to come up. So the fact that one couldn't compute the volume explicitly, one had to use the group structure of the group that was acting. The same thing happened in this situation. You had to find a way to do it in a way that didn't force you to actually write down the explicit inequalities. So now there's a method where you don't actually have to write down anything. And that's what I'm going to talk about tomorrow. A counting method, a general geometry of numbers method where there is a symmetry. You can use the symmetry to avoid writing down any of the actual inequalities, or actually computing any volumes or doing anything. So I'll talk about this method tomorrow. It was developed jointly with my student, Aril Shankar. For prehomogeneous cases, though, I'll mention what the idea was when I was doing the quintic case, is that there isn't just one fundamental domain in the world for the action of a group on a representation. There are many fundamental domains. And so, for example, if you take this whole fundamental domain and multiply it by some group element that's close to identity, this will just shift by a little bit. And so the idea is to not just count in one fundamental domain, but to count in a continuum of fundamental domains. So perturb this fundamental domain by epsilon, so that these cusps actually expand a little bit, right? And then divide. So count in this perturbed fundamental domain that thickens the cusps, and then divide by how much you perturbed, and that'll give, right? So you count in a continuum of fundamental domains, and then you divide by the measure of the continuum that you used, and that allows one to never actually have to write down any particular inequalities. And I'll talk more details of that tomorrow. But so what happens in the quintic case, though, is that you get 8 cusps now. Okay, it's not just 3. And each of those 8 cusps correspond to some kind of reducibility condition, like orders in quadratic direct sum cubic, and so on. And so you end up dividing the fundamental region into 160 pieces. And each of the pieces has the property that either the volume is negligible, and so you can show that the total number of points in there is negligible, or when the number of points is not negligible, then it turns out it corresponds to some kind of reducibility condition, and so you can throw it out for that reason. And so all that gets left is the main body, and in the main body you show that it contains only S5 quartic orders up to negligible amounts. And then you compute the volume, and then you do the sieve to maximal orders. And that's what gives this result, the number of quintic fields. And here you don't have to put the S5 restriction. The total number of quintic fields of discriminant at most x is this constant times x. Okay. So what these two theorems say, and we already mentioned this yesterday, the number of quartic fields up to discriminant x, only about 90% of them have Galois group S4, and about 10% have Galois group D4. That's what Henri's results and this result together say. So this was kind of a surprise. Normally you expect if you pick a random number field, if you order them by discriminant, you still would have expected perhaps that 100% of them will have Galois group S4. But what this shows is that a positive proportion have Galois group D4, about 10%. Whereas for quintic fields, 100% of quintic fields, when ordered by discriminant, have Galois group S5. Okay, so you can sort of see what the pattern is in the constants. Right, so first we got 1 over zeta 2. That's the total number of quadratic fields, more or less, up to discriminant x. And then it's 1 over zeta 3, the total number of cubic fields up to discriminant x. And then people conjecture that it should involve zeta 4, but it's not true. But you get 5 over 24. So everyone see the pattern? Yeah, it sort of depends on how you, yeah, it should be, if you're counting up to isomorphism, yeah. So when I was doing these quintic computations, every time I did this computation to get through the sieve to count to maximal orders, this thing came out different, as you'd expect, because it's a 40-dimensional sieve. It gets a little complicated. And then eventually it started stabilizing to this. And so that's why I thought that's the answer. But I wanted a way of independently knowing that the answer that it was stabilizing to, there was a reason for that answer to be. And these 4 constants didn't seem to have an obvious pattern. And so that's what led to thinking about what should be the correct constants in these kinds of problems. And so I won't go into this in depth, but the idea of what these constants should be, I kind of finally figured out, and it's inspired by the Cohen-Lenstra heuristics in a sense. So suppose you take a random, say, quintic field, and you localize it at a prime p. Then there are various local ATAL extensions of QP that it could be. And what probability distribution do you expect on these local extensions? There are only finitely many local extensions that are quintic, right, of QP. And so they should have some kind of probability distribution on them. And what should that probability distribution be? Well, the principle is similar to that of Cohen-Lenstra and to what appears in the Siegel mass formula and the Dirichlet class number formula. It's the principle that algebraic objects tend to occur with a frequency that's proportional to 1 over the number of automorphisms. And so these constants, what they are in general, for degree n, for degree n Essen fields, I claim that we expect an Euler product where the factor at p reflects the fact that local extensions should occur in a proportion that's with a frequency that's proportional to 1 over the number of automorphisms. And so I'll tell you what the constant. So we expect a constant times x. The total number of degree n Sn fields up to discriminant x should be a constant times x. And the constant turns out to be this. And there's the heuristics behind why this happens. Basically, what I said, that objects should occur with a frequency that is proportional to 1 over the number of automorphisms. So what you do is you take 1/2 times a sum over all local extensions of, say, first of all, R, okay, ATAL extensions of degree n, and you take 1 over the number of automorphisms of those fields. Okay, and those are what these Archimedean factors are in these constants. And then you multiply it over all local places, finite local places. There's a factor of p minus 1 over p that comes up for natural reasons. And again, you get a similar count over. So it'll be a sum over all local extensions. So k of qp of degree n. And so again, you weight by the number of automorphisms of that field over qp. But then you also weight by 1 over the discriminant. Because we're counting by discriminant, if you have a high p power of discriminant, that's going to, right, if your discriminant is 1 over p to the 5, then you expect that to happen 1 over p to the 5 frequency. So you divide by 1 over the number of automorphisms times 1 over the discriminant. So as a power of p. Okay, and if you work this out, then you get exactly this sequence of constants. So expect this many times x having absolute discriminant. The half comes from the same thing that this p minus 1 over p comes from. So, so what is the so the discriminant is going to be a power of p, right, of this local extension. What is the probability that a number is exactly divisible by this amount of power of p? The answer is p minus 1 over p times 1 over the discriminant, right? So that's where the p minus 1 over p comes from. And the 1/2 comes from the same similar kind of thing. If you pick a random number, what is the probability that it has a given sign? Okay, 1/2. Yeah, so that's kind of the so that's what those mean. And you can actually one can actually explicitly evaluate these things using what's called Sayre's mass formula for totally ramified extensions. So one can generalize Sayre's mass formula to actually evaluate these things explicitly. So that constant turns out to be, so this constant here turns out to be the number of 2 torsion elements in Sn divided by 2 times n factorial. So that's the Archimedean factor. So this thing evaluates to this. So this is the Archimedean factor. So if you check for 4, you should get 5 over 24. That's the Archimedean factor. And then what you get at the finite primes involves the partition function. So q, k, n minus k. So this is the sum from k equals 0 to n, okay, of qk n minus k. So this means the number of partitions of k into at most n minus k parts. So you take qk n minus k minus q k minus 1 n minus k minus 1 divided by p to the k. So remember, q is the restricted partition function. A number of partitions of k into at most n minus k parts. You subtract the number of partitions of k minus 1 into at most n minus k plus 1 parts, and you divide by p to the k. And so you get some finite Taylor series in 1 over p here. And that's exactly these finite Taylor series in 1 over p you get here when you evaluate it. And so that's sort of an explanation of where these constants are coming from. And as Henri said yesterday, this can be evaluated to arbitrarily many decimal places quite quickly, depending on the arbitrary. Okay. Okay. Any questions on? I kind of said this all quickly, but there's is the number of 2 torsion elements in Sn, including the identity. Yeah. Yeah. So if you're interested in these kinds of mass formulas, there's a paper that I wrote in IMRN that sort of does these evaluations and works out why it turns out to be this. So these constants that appear in these theorems really reflect local counts. And you take a product of these local counts, and that's what gives you the global count. So they sort of give you these local global principles. And that happens in all the cases that I'm going to be talking about later.
Does it isolate the Sn extensions?
I mean, from the point of view of these counting things, the generic things are what end up being counted. All the cuspidal stuff. I mean, this formula comes naturally from if there were spaces that we knew that corresponded to higher degree number fields, then this is the formula that would come out, because it would only count the generic extensions that lie in the main body. But I see what you're asking. Why isn't it including the D4 fields for n equals 4? Yeah, I mean, that's this is what happens. Yeah. Oh, exactly. Yeah. So this formula works totally generally, and it can be proved up to n equals 5 if you decide to restrict your local, the local things you allow at the reals or at the prime 7. Then you just take the appropriate sum just over those extensions, and that gives the right asymptotic. And that can be proven up to n equals 5. And so this really, each of the individual summands that appear here really is reflecting that amount of the local stuff at that prime. Yeah, that's right. And even if you do it for infinitely many places, it seems to always give the right answer. And even that can be proved in many cases. So when you're going to have zero density of stuff, it's only when the amount of stuff that you're taking out at every prime causes this to converge to 0. And so far, even for all infinite kinds of things that I've seen, it actually gives the right thing in cases that you can prove. Yeah, right, exactly, right. So sometimes the sieve can handle even infinitely many local conditions. Okay, so as I said, there are about 36 different spaces that one can try to do this with. Some are of more interest to number theorists than others. I'll mention a couple more that I think would be of interest to this audience. So remember the duality between quartic fields and 2 torsion in the class groups of cubic fields. That allows one to prove a case of the Cohen-Martinet heuristics for cubic fields. So the mean size of the 2 torsion subgroup of the class group of totally real cubic fields turns out to be 5/4. This is something that was predicted by Cohen-Martinet. It's the case that Henri talked about yesterday that was in doubt because, well, cubic fields do have all the second roots of unity. And so there was doubt that maybe this wouldn't be true there, but it turns out to be true. And the analog for complex cubic fields is that, well, the average number of two torsion elements in the complex cubic fields grows a little bit, as you'd expect, and it's 3/2. And that also comes just by taking the quartic space here and looking at the dual representation, but the same count applies. So that's from the duality that I talked about yesterday. So as a consequence, since the average number of two torsion elements is 5/4 on average in the class groups of totally real cubic fields, what that means is that at least, well, 3/4 of totally real cubic fields and at least half of complex cubic fields, for the same reason, have odd class number. Okay, so most cubic fields have odd class number, which has some applications. Yeah, so this proves the only known case of the Cohen-Martinet heuristics for higher degree fields. Okay, maybe I'll mention one more. So as I mentioned earlier, Gauss had conjectured these. Those are called the Gauss-Siegel class number summation formula. It tells you how the class number times regulator behaves on average as you vary over quadratic fields, right? And class number times regulator you expect to be about discriminant to the 1/2. And if you sum over discriminants up to x, then you expect about x to the 3/2. Right? So that was proven by Mertens and then by Siegel for the real quadratic case. But now that we have an analog of Gauss composition for cubic fields, one can prove an analogous thing for cubic fields. Namely, if you take the class number times the regulator over all cubic fields of discriminant less than x, then you get a constant times x to the 3/2, where the constant is explicit and in fact has an interpretation just like of a similar kind to this. This is still being written up, but so it actually gives a conjecture of what should happen for general number fields also in terms of mass formulas of this type. But now you have to take into account the units of the number field and the units of the localizations and their measures, and that's what comes in. So the constant has a very nice interpretation. It gives the right thing for quadratic fields as well. It gives the right thing for cubic fields, and so you expect that that would continue as well. Okay, so I think maybe I'll stop with on prehomogeneous stuff, since I wanted to move on to some non-prehomogeneous things. But any questions about prehomogeneous things? Yeah.
Well, I'm not sure whether it is a prehomogeneous question, but do you have this such a theorem for cyclic cubics also, if you isolate the cyclic ones?
I didn't try. Yeah, I think it's possible. Although I didn't work it out, but but it is possible to do. Yeah, because it turns out this representation has a certain has a prehomogeneous subspace for a slightly smaller group. It isolates the cyclic things, and so you can do a count on those as well. Yeah. Oh yeah.
Could you please say a little bit about how you begin to count these things in theorem 11?
By similar methods, except now you have stabilizers, so the orders of the stabilizers come into play, and that's why the regulator shows up. So these prehomogeneous vector spaces I was talking about had finite stabilizers. The one that corresponds to this, namely pairs of 3x3 matrices, they have a GL1 stabilizer, and the measure of that stabilizer over Z is what gives the regulator. Yeah. But the cyclic question that you asked, that's a good thing to point out, namely that there are other prehomogeneous vector spaces that are not on these tables, namely because the ones that have been classified in that work of Sato and Kimura I mentioned are those that satisfy certain conditions, namely reductive group and irreducible representation and so on. If you drop these conditions, then there are lots of prehomogeneous vector spaces in the world, and I think it's a very interesting representation theoretic problem to classify those. But for example, the cyclic cubic case corresponds to a non-reductive representation, in which the counting techniques still apply. And so I think it's a very interesting problem to understand non-reductive representations, because they also often correspond to interesting algebraic objects as well. So I hope that's something that we'll get to think about a little bit this semester. Non-reductive representations. Okay. But instead of dropping the reductiveness and irreducibility of representations, I thought I'd start saying a little bit about non-prehomogeneous representations. So what are the kind of objects that are parametrized by prehomogeneous things? They parameterize things that become trivial over the complex numbers. So things like number fields and class groups. These are things that would be parameterized by prehomogeneous vector spaces. So if we find more prehomogeneous vector spaces, we may be able to parameterize higher degree number fields or different kinds of class groups and modules, and so on. And that's a very interesting question. But if we want to go on to objects that have moduli over the complex numbers, for example, algebraic curves, where even over the complex numbers there can be many isomorphism classes of genus 1 curves, for example. Whereas for number fields, there's only, if you're talking about étale quintic extensions, there's only one étale quintic extension of the complex numbers, namely c to the 5. So there's sort of two directions that one can go from these tables of prehomogeneous vector spaces. One can drop the reductivity condition but stay prehomogeneous, and we'd be able to get more parameterizations of algebraic objects that become trivial over C, so things involving number fields. But then the other direction we can go is look at representations that are not prehomogeneous, and those could correspond to objects that even over C, there's more than one isomorphism class of. For example, genus 1 curves or elliptic curves. Okay, so that's kind of what I said there. Okay, so prehomogeneous vector spaces correspond to things that are trivial over C. Just think of it that way. And so now the question is, can we start looking at non-prehomogeneous representations and look at the integral orbits there, and maybe they'd correspond to interesting algebraic objects in which there's more than one isomorphism class even over C. So can we parameterize such algebraic objects and then gather information about the statistics of those objects by developing counting methods for more general representations? Yeah. That's right. That's right. Yeah, that's right. Yeah, when representations have stabilizers, nobody knows how to make a fundamental domain. Yeah, right. So it's kind of like the problem of, can one develop a fundamental domain for the action of GL2Z on real binary quadratic forms? If we knew how to do that, then we'd be able to solve. Well, we don't know if that's. I mean, yeah, whether there is even a fundamental domain, right? It's going to be a very thin kind of thing. You expect class number to be 1 most of the time, and so it's going to be some really thin, weird thing that's not a Euclidean region. So you make something that is a Euclidean region, and then the stabilizer naturally comes up into it. And that's why the class number and regulator are so hard to separate. Yeah. Okay, so if we had non-prehomogeneous representations, then those things would, if they parameterize things, they'd parameterize things that have more than one isomorphism type over C. So, for example, algebraic curves. In particular, curves of genus 1, curves of general genus, and higher dimensional varieties, and so on. So, okay, so what is the next sort of case that's natural to look at beyond prehomogeneous? Well, one way to think of prehomogeneous vector spaces is that they're representations in which the ring of invariance is generated by one element. Okay, like binary quadratic forms, the ring of invariance was generated by just the discriminant. The same happened for binary cubic forms, and in all the representations that I wrote for you, they all have one invariant. And the ring of invariance is just generated freely by that one invariant. So a natural generalization of such representations are those having a free ring of invariance, but there may be more than one. So this is, from the counting point of view, that's the reason that I started looking at this, is because it's sort of a natural next generalization of prehomogeneous vector spaces. But I should mention that there are many interesting representations that go beyond this, where it's not free, that have already been studied, for example, in Melanie Wood's thesis, and also by Kevin Wilson, who's been looking at some, and Wei Ho. So they all have very interesting representations that have more than one invariant, and where there are relations among the invariants. So that's a whole other area that still needs to be understood. But this is a natural place to start, where one can sort of again, completely classifies such representations. So a G comma V, where G is an algebraic group, V is a representation, such that the ring of invariance is free. This is called a co-regular space, a co-regular representation. And the representation theorists, again, this is a natural thing to study from the representation theory point of view. And these spaces, again, under all these assumptions of irreducibility and semi-simplicity and so on. If you assume semi-simple and irreducible, these such representations that have a free ring invariance have been completely classified by Littleman in 1989. And turns out there are 70 of them, including 24 infinite families. Okay, so there are lots of examples, just even with these very natural niceness conditions of being semi-simple and irreducible. And if you drop those conditions, then there are lots and lots of them. And so here's the next goal, is look at these representations and understand, what do the integer orbits parameterize? Are there interesting arithmetic objects that they parameterize? But actually, there's even a first question. In the primogenous case, it wasn't so interesting to classify the complex orbits because there was just one. But here, it's already interesting to classify the complex orbits because there's more than one invariant. There are lots of isomorphism classes of complex orbits. And so even the complex orbits, what do they mean? Okay, do they have an interpretation? That has to be done first. Then one can go down to a general field, which I'll talk about today and tomorrow. You can go to a general field, and that's where some Galois cohomology comes in. And you can try to understand what the orbits over a general field mean, and then understand it in particular over Q. And then there's a hope of then trying to go over Z. Okay, so that's the long-term plan. So this is ongoing joint work with Wei. And what we show is that for co-regular representations, most of these semi-simple co-regular representations that appear in Littleman's classification correspond to genus 1 curves and data involving genus 1 curves. For example, line bundles and points on the Jacobian and so on. And just like 2 by 2 by 2 cubes were sort of the mother of all primogenous vector spaces, it turns out all co-regular spaces, well, they have two mothers, or mother and a father. I don't know. Okay, so one is the space of hypercubes, 2 by 2 by 2 by 2 matrices. 2 by 2 by 2 by 2 matrices turn out to be co-regular. They have a free ring of invariance, and then 3 by 3 by 3 cubes. So you can go from a 2 by 2 by 2 and either increase the number of dimensions or increase the size of the length of the cube. Okay. So these are sort of the two things that now you can do all those operations that I talked about to actually produce essentially all co-regular spaces. And so some of the things that come up, for example, if you totally symmetrize the 2 by 2 by 2 by 2 hypercube, you get binary quartic forms. Right? And if you totally symmetrize the 3 by 3 by 3 cube, you get ternary cubic forms. So these are also examples of co-regular spaces. Okay? And they're about, the ones that correspond to genus 1 curves, it turns out there are about 30 or 40 of them, I'd say. Probably, right? Yeah. Okay. So today I want to leave you thinking about hypercubes. So before I knew what co-regular spaces were, I was already excited about hypercubes because it was sort of the next thing after cubes. And I remember in Oberwolfach with John Cremona, we actually did computations that essentially proved that the space was co-regular when we didn't know what co-regular meant at the time. But the analogous question to what I asked for cubes is, well, what would happen if you put numbers on the corners of a hypercube? So, okay, that's the best I can do in drawing the hypercube. So there are 16 numbers on the corners of a hypercube. So when you have a hypercube, just like cubes, right? When you have now when you have a hypercube, there are various ways in which you can slice the hypercube into two cubes, right? There are 6 ways, if you can visualize that. Okay, so I gave one slicing already because I didn't have a choice. Okay, so if you have a hypercube, you can slice it into 2 by 2 by 2 cubes in essentially 4 different ways. Okay, so let's call it A1 and B1. And just like the trick we did for cubes, right? So once you have a slicing of a cube into 2 by 2 matrices, right? We took determinant of AX plus BY, right? And that gave a binary quadratic form. In this case, remember, a cube has a unique invariant also, right? It's primogenous, and its degree is 4. The way to see that is, remember, when you had a cube, you could slice it into 2 by 2 matrices. You could call them A and B. You could take determinant of AX plus BY. That gave a binary quadratic form. And then you could take the discriminant of that binary quadratic form. And that, if you work it out, that's degree 4, right? Because the determinant was degree 2, and then the discriminant of the binary quadratic is degree 2. And so it has total degree 4. So these two cubes have a degree 4 invariant, kind of analogous to the determinant, except it's now degree 4. And so remember, a 2 by 2 by cube has a unique SL2 cubed invariant called the discriminant, which has degree 4. And so if you have each slicing of a hypercube gives you 2 cubes, and then you can call them A1 and B1. Then you can take discriminant of A1x plus B1y, and that'll be a binary quartic form, right? Because it's 2 variables and it's degree 4. Okay. So what that means is that every hypercube gives rise to 4 binary quartic forms. Okay. Just like a cube gave rise to 3 binary quadratic forms, a hypercube gives rise to 4 binary quartic forms. Okay, this is kind of analogous. So now what is a binary? Just like a binary quadratic form corresponded to an ideal class in a quadratic field, what does a binary quartic form correspond to? Well, it yields a genus 1 curve, namely the double cover of P1 that has as ramification points the 4 roots of that binary quartic. So that's a genus 1 curve together with the degree 2 line bundle. Right? Okay. That's the way to think of it. And to actually see this genus 1 curve, you can actually see it just inside this hypercube. So another way to do, because now there are more ways to slice a hypercube. You can take a hypercube and you can slice it into, well, you can make a 2 by 2 matrix of 2 by 2 matrices. Okay. Okay, like that. So here's the hypercube has now been made into a 2 by 2 matrix of 2 by 2 matrices. And now, if you look at the determinant, so you can take x1 times this plus y1 times this, and then you can take x2 times this and y2 times this, and then you get 1, right? Or you can do them both simultaneously, and you get 1 2 by 2 matrix that you can take the determinant of in those 4 variables, x1, y1, and then x2, y2. And that gives you a 2 by 2 matrix at which you can take the determinant of. And if you take the discriminant of that polynomial in y1 and y2, that's exactly the binary quartic. But this thing gives you a bi-degree 2-2 curve in P1 cross P1, and that's genus 1. Okay. And if you take the discriminant in any of the 2 directions, you get the 2 binary quartics. So you get a genus 1 curve in P1 cross P1, and you can project to either one of the P1s, and those correspond to the 2 binary quartics that would have been coming out from that. This is the way we were slicing there. Okay, so this takes a little bit while to absorb. So I think that's a good thing to end on, just for you to think about that. I just want to mention one other way to think about this, and then, because this is kind of the basic construction that leads to understanding all of the co-regular spaces, is this kind of argument. So another way to think of a hypercube, right? It's a 2 by 2 by 2 by 2 matrix, and you can think of it as a quadrilinear form, right? So it's a quadrilinear form T that takes in 4 inputs, and these 4 inputs are in 4 2-dimensional vector spaces. I don't know if you can see this. Right, so it takes in 4 inputs. Okay, and these bi-degree 2-2 curves, what do they correspond to? They correspond, in P1 cross P1, they correspond to points in P1 cross P1. Okay, so if you plug in something here and plug in something here, then you're left with just a 2-2 form, which is a 2 by 2 matrix. Right, so if you plug in 2 variables for 2 of these dots, then what's left is a 2 by 2 matrix. And you can ask whether that's singular. So if you look at the set of all VW, okay, such that T VW dot dot, right, which you think of as a 2 by 2 matrix, is singular. Okay, then this is a genus 1 curve. The set of all is VW in P1 cross P1. So you're taking all pairs V and W such that if you stick them into this quadrilinear form, you get a singular 2 by 2 matrix. Okay? And that you can show as a genus 1 curve in P1 cross P1. Okay? Any questions about that? That's kind of a... Okay, so I'll leave people to think about that, and this will be the starting point to understand parameterization of genus 1 curves. Okay, and I'll stop there.